So, let's do, I'm going to check my homework really quick.
Okay.
Oh.
Are these kind of problems you're going to be able to verbalize to me?
Yeah.
Okay.
So, oh crap, we're doing these graphs. Hang on. I need to get up on that website thingy. TTP.
No.
There we go.
Okay. So you're going to a website?
Yeah.
Would it make it easier if I went to the website on my end?
Yeah, probably.
Can you send me the link? Do you know how to copy and paste it into the chat window of this GoToMeeting?
I probably can.
Okay.
Hang on.
Paste it into where it says type message here, and then when you hit enter, it'll go into that chat window.
Okay. Paste.
Yeah. Okay, let me click on that. See if...
Yeah.
Okay, what's your username?
So you're good. Yeah, it's GR1. Hey, Mom, can you get them, please?
GR1?
And then and then the password is, oh crap, I think it's 2076. And that should work.
Okay, looks like it did.
Yes. Then click on that book. And then we are in chapter 6 on the side, or actually chapter 7, and then do 7.1.1 right there.
Okay. Okay, so you're working with exponentials.
Yeah. So I guess we could start with that because we're doing that.
Okay. Now, do these have exercises at the end of them? In other words,
no, they just have like the answers that you can go look at.
I mean, what problems are we going to work on here? That's what I'm meaning.
Oh.
In other words, the way this generally works is that I don't act as the teacher in lecturing about this subject. The way it works best is that if you bring problems and we have problems we can go over.
And it's that we're just now beginning to learn that, but I'm not understanding what she said we're just investigating, but she had us do those problems and
which problem? Because there's all kinds of them here. There's this kind. So which ones would you like to look at?
Let's do 7.1.1. Go down. Down. Okay. Do the 7-10.
Okay, that problem there, okay. Bouncing ball?
Yeah.
Alright. Hold on, let me get it.
Let me grab a pen really quick.
Okay.
Okay, go ahead.
Okay. So, if you drop a ball from 160 centimeter height and it rebounds to 120 centimeters on the first bounce, what percentage is it bouncing up?
I don't know.
Or what fraction? the fraction would be 120 divided by
Over.
160, which is 3/4. In
Oh.
other words, every time the ball bounces, it bounces 3/4 as high as the previous bounce.
Okay.
Okay? And you can model its height at any point in time by taking that ratio to the nth power, where n is the bounce. In other words, on the second bounce, well, hold on just a second, I left something out there, times the initial height. So
okay.
the height at any point in time is going to be that. In other words, on bounce 1, we're going to multiply, n is going to be 1. We're going to have 3/4 times 160, which will give us the 120. Okay? On bounce 2, it would be 160 times 3/4 times another 3/4, which is going to be 3/4 of 120, which would be 90. So on bounce, do you have your calculator?
Yeah.
Okay, go ahead and calculate what the 5th bounce would be.
I don't know how to put a fraction into my calculator.
Okay, put in 0.75 raised to the 5th power. Do you have this little, what kind, you have a TI-84 or 83?
83.
Yeah. 0.75 is 3/4. And raise it to the 5th power will be 3/4 to the 5th power.
How do you, oh. I got it. So then you have to do that, wait a minute. You have to do,
If you do 0.75 to the 5th power, multiply that number by 160, you'll have what it is on the 5th bounce.
on the 5th bounce?
Uh-huh. Because we've taken 3/4 to the 5th power.
Oh.
In other words,
Okay.
on the second bounce, n was 2. So we had 3/4 times 3/4. But on the 5th bounce, it's going to be 3/4 times 3/4 times 3/4 times 3/4. That was really the way they wanted us to do the problem. I see now that they asked C, what is it on the nth bounce? And this is what it is on the nth bounce, what I've circled. But
the 8 equals 160.
yeah, the height is going to be equal to 160 times the bounce ratio, if you want to call that the bounce ratio. With a Super Ball, you might have a 90% bounce ratio, where it always bounces up 90% of what it was the previous height. There's no such thing as a bounce ratio greater than 1. In other words, there's no ball that will bounce higher than it's dropped from. But
Right.
so for the 5th bounce, it's 160 times 3/4 times 5 times, which is the same as 160 times 3/4 to the 5th power.
Wow.
So what did you get when you did 3/4 to the 5th power?
37.96.
So that would be 0.379? Oh, time.
No.
Oh, and then you multiplied it by 160 and you got 37.9?
Yeah.
Okay.
37.96.
So the 5th bounce bounces up to 37.96 centimeters.
Okay.
Okay. And then the nth bounce is that. It's an exponential expression.
That makes sense. I didn't know what to do with that one. I was like, I
Well,
don't know where to start.
Let's talk about exponential expressions because they're not algebraic expressions.
Okay.
if we have this is what your book or this chapter starts out with b being greater than 0. And if I say that 8 equals 2 to the third power, that's an exponential expression. Okay?
Right.
Now, the thing is that we don't have algebraic ways of solving exponential expressions. If I say y equals 2 to the 3.1 power, I have no idea what that is. I know it's a little bit more than 8, but it's not up to 16, so it's somewhere in between. But I don't have a way of figuring it out. In the same way that, I don't have an algebraic way of figuring it out. In the same way that if I said 10 is equal to 3 to the x, what is x? You don't know how to figure that out. You know that x is a little bit more than 2, right? Because 3 squared would be 9. But 3 cubed would be 27. So if I was guessing here, I would say x is probably about 2.1. If you took 3 and raised it to the 2.1 power, you'd get somewhere around 10. That's my guess. Okay? But this is a key thing to understand about exponential expressions is they're not algebraic. In order to solve these, we have to actually introduce the concept of logs. Do you get logs in this chapter?
No.
No, okay.
Well,
So
I don't know what logs are.
Well, logs are kind of the way you solve these. But I would be surprised if you were getting logs in Algebra 1. You'll get logs in Algebra 2 for sure. I thought maybe they'd introduce them to you, especially since they start talking about exponential expressions, because we don't have any way to solve this without logs.
Yeah, okay.
But anyway, that's just a little bit about exponential expressions. Let's look. Should we just go down and 7-11, or you want to pick others? A little more conventional algebra would be 7-12.
Yeah, like I don't know how to do 7-12 like B, because I'm never really good with fractions. And then the only rule that I know about that one is if it's a negative on top, you have to switch it to put it on bottom to make it positive.
Correct.
That's the only thing I know.
These are easy. I'm going to teach you everything you need to know today about these. First of all, let's talk about exponents. If I say that b to the second times b to the third, if I am multiplying the same base to different exponents, then I'm going to add the exponents, which is equal to b to the fifth. That's rule number 1.
Okay.
Rule number 2 is if I'm dividing, and instead of putting numbers on them, I'm going to put letters on them. If I'm dividing the same base, I'm going to subtract the exponents. And if I'm doing something called exponentiation, where I take it to a power and take it to another power, like problem B, or even problem A, I multiply the exponents. So between those 3 rules, and let's change this to x and y, so you'll have the generic rule. Notice that we're always doing one level less with the exponents than we're doing with the base. In other words, when I'm multiplying the base, I'm adding the exponents, and I tend to think of addition as one level less than multiplication. When we're dividing the base, we're subtracting the exponents, which I think of as one level less than division. And when we're exponentiating, we're multiplying, which is one level less than exponentiation. So there's the three rules. Let me number them 1, 2, and 3, and then let's look at. Well, first let's look at problem A.
Okay.
Now, because everything is in the parentheses, everything is going to get acted upon by this top exponent too. So you basically have to square everything inside here, term by term. So what is 3 squared?
9.
What is x squared squared?
Is it x to the 4th?
Yeah, because of rule 3. What is the next term?
Y the
Well, y squared. We have to square the y term.
Oh, okay.
And then z to the what?
32.
No, so all you have to do is multiply the 2 times the 4.
Oh, 8. I was doing 4 times 4.
Okay, now let's look at B. Again, we're going to treat every term in the numerator and every term in the denominator separately. There's actually a few ways we could do this problem. There's not just one way. Let's do it starting by applying the cube to every term in both the numerator and the denominator. What do you get? What do you get in the numerator?
Wait a minute.
I'm going to cube everything I see here in top and bottom. I got 2 choices. I could simplify this first, but let's do it the other way, and then I'll do it the first way, and I'll show you that there's no difference. So first of all, let's take the cube and act on the numerator. So what is going to be in the r in the numerator?
It's not 5, is it?
6. It's rule 3. Do you see why it's rule 3?
I don't know what rule 3 is.
Are you looking at my screen?
Yeah.
Rule 3 says that if you have a base that's taken to an exponent x, and you raise it to another exponent y, then you multiply the 2 exponents together.
Okay.
That's what rule 3 means, is it applies to this situation here. And then the exponent on s is actually 1, right?
Yeah. So it's S3.
And now apply it to the bottom also.
R to the 3rd. And S to the, is it the 27th or is it the 9th?
9th. Remember, we're multiplying the exponents. We're not cubing them. In other words, this rule right here applies to the bottom as well as the top. So I'm going to multiply 3 times 3 to get s to the 9th. And then, t to the 3rd. Okay, now we have to reduce that because that's got some letters that, in other words, I've got an r to the 6th over an r to the 3rd. What does that net out at?
1/2? Or no, 2 over 1.
No, rule number 2.
Oh, R3.
There you go. In other words, so I can erase my r to the 6th and my r to the 3rd and make it r to the 3. It's in the numerator. Okay? How about the s's? We've got s to the 3rd over s to the 9th. What's that going to be equal to? S to what?
-6.
Correct. But that would be if it was in the numerator.
So you got to put it on the bottom.
So I'll put it on the bottom with a +6 on it. And the t is only in the denominator. It's not in the numerator, so there's nothing more to be done with it. And there's our final answer. Now,
Yeah.
you could write it like this. R cubed s to the minus 6 t to the minus third. But a lot of times on your tests, they'll tell you no negative exponents in your answers.
Yeah, they do.
They do tell you that? Okay. So you want to end up turning it into positive exponents. So what is this equal to? 1 over x to the minus 6.
I don't know.
You can always do this. You can always do that.
Oh.
In the
okay.
same way that if I'd have said, what is x to the minus 6, you would have said it's 1 over x to the 6th. So changing this thing from minus to plus merely means flipping the thing. So
Okay.
1 over x to the minus 5th is the same as x to the positive 5th, like that.
Okay.
Okay? All right. Let's tackle number C. Okay, hold on a second. Let me see if we're done with exponentials. Yeah, we kind of are. Let me erase these 3 rules, or go down 1 at least. They've taught you FOIL.
I forgot what it was, but yeah.
Well, I don't really like the terminology anyway. It stands for first, outside, I is inside, and L is last. What they mean by that is I'm going to multiply the first 2 terms first, then I'm going to multiply the 2 outside terms next, then I'm going to do the 2 inside terms, and finally I'm going to do the 2 last terms. Okay?
Yeah.
I prefer what I call ET. Here, let me write it like this. ET. What does ET stand for? Every term by every term. The reason I like ET better is because it will handle it when you have more than 2 terms that you're multiplying. FOIL works perfectly fine for a binomial term multiplied by another binomial term.
Well, and the way that I do it is I do like 3m times 2m, and then I do 3m times -1, and then I do 7 times 2m, and then 7 times -1.
Great, and that's exactly how you should do it. So multiply this for me. Doing every term by every term, which was what you described right there was every term by every term. And be methodical about it. In other words, use a system that's consistent. So you'd always do it the same way every time?
Yeah.
So what would you multiply first?
A times x and then a times y.
What's next?
B times x and b times y.
And finally?
C times x and c times y.
See, ET works there, but FOIL wouldn't mean anything. So ET works both with binomials, trinomials. I could have 5 terms by 6 terms. And as long as I multiplied every term by every term, that's what I have to do. So what do we...
They just wanted to be creative about it.
Yeah, they wanted to come up with a clever name, and FOIL is more clever than ET. Unless it's 1985 and ET just came out. But
yeah.
so what's 3m times 2m?
6m squared.
What's the rest of it?
M times -1, so that's -3m. And then plus 14m, and then -7.
Okay, and now simplify that.
6m squared plus 11m -7.
Good. All right. X minus 3, the quantity squared. What's that equal to?
X squared. I gotta look at your rules.
Oh, actually, my rules didn't have anything to do with this. In other words, this is the same as x minus 3 times x minus 3. That's all it is.
Oh. So -3 times -3 is
Well, hold on.
-9. So plus 9.
ET.
No.
ET this.
Oh. X times -3 minus 3x. And then minus 3x. Plus 9.
Okay. So we've got x squared minus 6x plus 9.
Oh.
Okay. Now, unless I gave you some rules the other day, I might have, because there is a nice thing to remember. And that's, without having to FOIL this every time, it's nice to remember that that's always going to be that. And the other half of that to remember is the subtraction. And the reason this is nice to remember is because you're going to have to do this about 1,000 times over the next 3 years, where you have a binomial that has to be squared. So rather than every single time going through the FOILing or ET process, it's nice to memorize these. And sometimes you'll get it presented to you like that, and you'll need to factor it back into this. So let's do an example so you'll know what I'm talking about here. If I said, what is x plus 2 squared? Use this, x is a, b is 2. So what's the answer going to be?
What?
Okay.
Oh, it's x squared plus is it 4x squared?
Just 4x?
No.
Because it's 2 times x times 2. So it's 4x.
Okay. Plus 4?
Uh-huh. Now that's the same thing you would have gotten had you FOILed it. If you multiply x plus 2 times x plus 2, you end up with this. But the first time through, you have 2 terms in the middle, and then you have to simplify it. So there's kind of extra steps when you do it the hard way. When you do it this way, especially if you get to a point where you memorize this, then these become a lot easier to do. And they get more complicated if I wanted to know how to do this. Use the same model, only A is 3x and B is 4y. So what do I get?
3x, no, 9x squared. And then, is it 4 times 4 or 2 times 4?
Well, it's 3x times 4y times 2. So it was, in other words, the 2ab would be 2 times 3x, that's the a. The b is 4y. Multiply all three of those numbers, you get 24xy. So that's the middle term, 24xy. And what's the last term going to be?
Wait, how did you get 24?
2 times 3 times 4.
Okay.
And then x times y.
Oh. Wow, that's confusing.
Well, you just multiply all the terms together. In other words,
Well, what would you...
I multiply all the numbers together and I multiply the two variables together.
Okay.
Okay. So what's the last term? The b squared part of it? In other words, this part?
I thought that was what we had to do.
Well, we're not done yet. There's 3 terms in the answer. There's that term, there's that term, and there's this term. We've got that term and that term. We need the b squared part. What is
but
b?
But that would be y squared.
B is...
That would be y.
Right. B is 4y, so that's going to be 16y squared.
But I thought we just did that with the 24.
No, that was for the middle term. Look at these formulas. The answer is a squared plus 2ab. 2ab was 24xy. All right, this is probably a little more advanced than what you're doing right now. I just kind of wanted to introduce that to you because at some point you're going to want to be able to do those problems like that. Let's go back. Let's go back and look at more of the stuff you're working on in class.
Can you do 7-13?
Sure.
Or, yeah, show me.
Yeah, no, I know what you mean, yeah. If 150 empty water bottles weigh 4.5 pounds, what would you expect 90 empty water bottles to weigh? Well...
So, you would start with, like, 150 times 4.5, right?
Actually, it's a ratio problem.
Oh.
It's a ratio problem, and that I'm going to say 150 is to 4.5 as 90 is to x. In other words, the ratios have to be the same. We certainly, if I said to you, how much would 300 empty water bottles weigh, what would the answer be?
300 over 9?
Yeah. In other words, twice as much, right?
Yeah.
Okay. Well, this case, they're giving us a number that's not a particularly, it's not a multiple of 150, it's a fraction of 150. So it's a little harder to solve, but it's still a ratio problem. In other words, it's still, whatever this ratio is, no matter how many empty bottles I have, it's going to be in that ratio. And now, how do I solve this equation?
Cross multiply?
Yep. So I get 150x equals 405, maybe?
90 times 4.5?
Do you have your calculator?
Yeah, I'm going to check it. 90 times 4.5. It's 405. Yeah, you're right. Wow, that was good.
and then divide that by 150. What do you get?
405 divided by 150. 2.7.
There's your answer. So that's what 90 empty water bottles would weigh, is 2.7. Now, I'm a little curious about stuff I'm seeing on this page. These help. In other words, if you don't know how to do it and you click that, it'll give you information?
Yeah, it'll like, if you click on it, it will load you up to a new tab, and then
oh, okay.
it'll give you a hint.
It isolates the
But
problem.
the thing,
And if I want to
yeah, but the thing is, sometimes I don't understand it.
Let's see what their hint is. Set up a proportion, okay? Their proportion is what I called a ratio. And another way to write it, maybe the way they would write it would be like this. It's actually much easier if you write it as ratios, but you might have gotten something like this. 150 is to 4.5 as 90 is to x. The thing is, we don't have any algebra to handle that. So whenever you have proportions, you want to set them up as ratios, and then you have equations which you can solve.
Okay.
Okay.
See, the bad thing about that is, like, I'm a visual learner, so I kind of have to see it to understand it. So when they do words and stuff like that, I don't always get what they're trying to say.
Yeah.
And then they give me the answer, and so I have to go, like, I don't just leave it off at the answer because you have to show your work, right?
Right.
So I try and figure out how they got it, and sometimes I don't understand anyway.
Well, just always make sure that when we're working, if you don't understand something I'm saying, that you stop me and don't let me go on.
Yeah.
Okay? That's really vital. Because I'm pretty sure that I can get you to understand just about anything as long as I get feedback from you, that whether you get what I'm saying or not, and so forth. So 714 is kind of a generic question about exponential functions.
Yeah, I think B is the one that I struggle with, because I already did A, but B is the one that I struggle with because it's with fractions. And I've just never been good at fractions.
If B is larger than 1, so that you have this, B is 2, any number that's greater than 1, as you start increasing x, it gets bigger, right? In other words, if x is 2, this becomes 4. If x is 3, this becomes 8. If x is 4, this becomes 16. So as long as this number right here is greater than 1, this gets bigger, and the graph looks like this. With this being the x-axis, this being the y-axis. Right. So as x gets larger, y gets larger. If you make b less than 1, say 1/2, any number between 0 and 1, as x gets larger, y gets smaller, and it looks like this. Think about it. If x is 2, you have 1/2 times 1/2, which is equal to 1/4. 1/4 is smaller than 1/2. If x is 3, you have another 1/2, and now you have 1/8. So as x grows, y gets smaller. All because whatever is being exponentiated is between 0 and 1.
How did you get 1/8 though?
Well,
I don't,
if you do 1/2 times 1/2 times 1/2, when you're multiplying fractions, you just multiply tops and bottoms. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8.
Oh, okay.
And I did it 3 times because I was doing 1/2 to the 3rd power. In other words, when x was equal to 3, y was equal to 1/8. When x is equal to 4, y is even smaller. It's equal to 1/16 as we go to the right on the number line. And that's why the graph goes from big to little.
Okay.
Okay?
Wait,
So
was that A or was that problem A or B?
that was, we talked about A when I had 2 up here. In other words, when I had a number greater than 1, it got bigger.
Wait, Y got bigger?
Yes. In other words, the graph for this function looks like this. It goes from lower left to upper right. It grows as x goes to the right.
Okay.
But the graph of this function gets smaller. Goes like that. Because as x goes to the right, y goes down. It gets smaller. So that's the 2 main situations, is where B is, when I say B, I mean whatever's in these parentheses here, when it's greater than 1 or when it's less than 1. Now, question C says, well, what happens when it's equal to 1? Well, 1 to any power is 1. That's what it looks like. Basically a horizontal flat line. If I have y equal 1 to the x. Notice that as x is 2, it's still 1. If x is 10, it's still 1. So pretty much, when it's equal to 1, you don't have to worry about that. That rarely comes up in math. But knowing these 2 here is very important. It's very important to understand that when you, just for example, square a number greater than 1, it gets bigger. If I square that number right there, it gets bigger. It becomes 9. If I square a number smaller than 1, it gets smaller.
I'm confused.
Okay.
Well, I got the concept of 3 squared equals 9.
Okay.
But when you start throwing
1/4.
fractions
Well, 1/4 squared means 1/4 times 1/4. It's straightforward. And when you multiply fractions, you multiply numerators and you multiply denominators.
Okay.
All right. Let's talk about multiplying fractions and dividing fractions. What is this equal to?
6/8.
6/15.
Oh, I don't know why I said 6/8.
Okay. We're multiplying numerators, multiplying denominators. Okay.
Uh-oh.
What's that equal? Don't say uh-oh. This is very simple. You just have to follow a pattern and know what this means. When you divide by a fraction, it is the same as multiplying by the reciprocal of that fraction. So this problem is very simple. It's 2/5 times 7/4. And that's the way we do all division by fractions, is we always turn it into a multiplication problem. And what's that answer?
14 20ths?
Which reduces to 7/10. Okay? So no matter how complicated the fraction, multiplying and dividing fractions is so much easier than adding fractions. This is a hard problem compared to multiplication. If I was multiplying these two fractions, I would just multiply tops, multiply bottoms. But when I am adding them, it's a much more difficult problem. Adding or subtracting is far harder than multiplication or division. What do I have to do to add these?
Find a common denominator.
And what's the common denominator going to be?
10.
And the term on the left, how many tenths is that?
4.
And the term on the right, how many tenths is that?
15.
And what's the result of that?
19/20th?
No?
No, 19/10th.
Right. Once you've found the common denominator, it stays the whole problem. In other words, your final answer is you merely act on the numerator, the 4 and the 15, not the denominator. But notice that this was a much harder process than multiplying these things. So, if you're going to say, uh-oh, on any problem, it would be an addition or a subtraction problem, not a division or a multiplication problem.
Okay.
Okay?
Can we do 7/16?
Sure.
The one where she's talking about the
Uh-huh.
yucky tuna sandwiches. Or no, yeah, it's 17. I don't get that at all.
Okay. Let me have a
I
read.
did the scatter plot, but no.
Okay. So each day, so let's see, the first day 12% of the surface of one sandwich had mold on it. She threw the sandwich out. She kept coming back. Each time she measured somebody else's sandwich and threw it out. Okay, so what's happening is that all of the sandwiches had mold on it when she got back.
Yeah.
Each one was covered by about a 12th. Or not a 12th, about an 1/8. 12% is about an 1/8. 12.5% is exactly 1/8. But 12% of each sandwich was covered with mold. She threw one of them out. Came back on day 2, checked somebody else's sandwich, and it had 15% mold on it. So if I do a scatter plot, with this being the days and this being the percentage mold, well, on day 1 it was 12. On day 2 it was 15. On day 3 it was 13. On day 4 it was 26. On day 5, oh, day 4. They got 3 day 4s in here. Interesting. So each time she measured somebody else's sandwich, she collected the following data. Okay. So on day 4, there's actually 3 different. There's 26%, there's 27%, and there's 24%.
That would be a cluster.
It would be, and it also means it's not a function because you have multiple y values for a given x value. And in day 5, she noticed that 38%, way up here,
Okay.
where I've just approximated these. I don't know if they're accurate or not, but once I've drawn this scatter plot, create a scatter plot and sketch it. Is a linear model reasonable?
Yes.
Not really. If a linear model, if I try to draw a straight line between the first point and the last point, I don't have any of these other points anywhere near my straight line. And that's kind of what it means, is a linear model reasonable. If I try to draw a line through those points as accurately as I can estimate, what's it look like? What kind of function is that?
Quadratic?
That is not a quadratic, that is an exponential function, the subject of this chapter. That's why I knew that it was exponential fit, not linear. Remember when we talked last week about regression models?
Yeah.
We talked about linear regression, and then we said that your calculator also would let you do quadratic regression, and it would let you do exponential regression, logarithmic regression, all of those. So when you have a scatter plot, the only reason I know that it's exponential, other than actually plotting it and drawing my best fit line through it, and I can see that that looks like an exponential. In other words, that looks like y equal b to the x, right? Mm-hmm. That's what we've been looking at all day today, is curves that go either low to high, or if b is less than 1, it would go like that. But in this case, obviously, there's growth going on. And in fact, bacterial growth is one of the perfect illustrations of exponential growth. A lot of things in the world have exponential growth or exponential decay. But exponential decay would be where b is less than 1, and that would describe stuff like plutonium, that loses its mass with time. As time goes on, any amount of radioactive material gets less. Eventually it just completely decays away. But you have two types of exponential behavior. You have exponential growth, and you have exponential decay. This is clearly growth, which you would expect, because that's what happens to an egg salad sandwich when you leave it out. Is bacteria and mold get on it, and they grow like wildfire. Notice that it took a whole week. They were out for 1 week, right? No, it doesn't say. Mm-hmm. Yeah, they were out for, just the weekend. And in the weekend, they're only 12%. But by day 5, it was 38%, which is a large jump. That's more than threefold. Okay, so let's answer B. Based on the story, what kind of equation do you think will best fit the situation? Well, we've already said an exponential equation. And C, fit the data with the exponential model and write the equation. What percentage of a sandwich did Hannah predict was covered on Wednesday? Oh, which isn't listed. That would be day 3. In other words, what would that be, percentage? Read it off the graph. Not sure how she wants you to do that. She wants you to do this problem on your calculator?
We could.
Well, we don't have enough time to really go through that. We only got 5 more minutes.
Yeah.
Let's talk about what percentage of a sandwich did Hannah predict was covered on Wednesday? Well, clearly somewhere between 13 and 26%, right?
Yeah.
And if I look at my chart, I mean, there's 13%. Here's 26%. So wherever that would fall, maybe, I don't know. I don't know if she wants you to guess or figure it out, but we'll guess 16%. If you were to draw this, if you were to put this scatter plot in on your calculator and request an exponential regression, you will get an equation like this. And once you get the model where you have A and B, say you get y equals 0.2 times 3 to the x power. In other words, that's the kind of an equation your calculator gives you back when you give it a scatter plot and say, do an exponential regression for me. You'll get something back like this that gives you what the value of A is and it gives you what the value of B is. Once you have those two numbers, well, now we can actually calculate what percentage would be left on day 3 by plugging it into this equation. I would plug in 3 for x and whatever y would be. But that's pretty sophisticated stuff. And isn't stuff that we want to spend all of our time on. Linear and exponential regression and all of that. It's useful to know. You're going to need to know it, but that's not the main thing you need to know from Algebra 1. All right, why don't we wrap it up there? And this is good. This is good that your material is online because it makes it real easy for us to bring it up when we have a session. Okay. What does your dad want me to do regarding payment? Is he going to use PayPal or do you want to...
My mom's going to use the PayPal. She keeps on saying that she's going to like go on there, so she
okay. Let me just give her, in order to pay me with PayPal, you just have to go into your PayPal account and send a payment to my email address. That is my PayPal account. Is my email address.
Wait, I gotta write this down.
Okay.
At gmail.com. Okay. So that's where you send it to. Okay.
Yeah, and I don't, if you like, I can send you an invoice, but I don't really need to. If it's an hour session, it's $32. If it's only a half-hour session, it's $16.
Okay.
Okay?
Okay.
And, yeah, I think this will work good. I have recorded this session, and that should be useful to you. Just, you know, if you are looking back on it and are confused and don't remember some of the stuff we covered, you'll be able to go back and cover it.
Okay.
Where do I have your email, or do I have an email address which I'm going to need in order to send you the link? Give me an email address where I can send the link for this recorded session to.
Okay, go to, so do RAB.
Oh, we did this last time, didn't we?
Yeah.
Okay.
LISS.
I have it in my Google then. So
okay.
I know where to send it. Yeah, I sent you the last one, didn't I? Yeah. I don't know if you had a chance to watch it or not, but it's worth taking a look at it just to see how it works.
Okay.
And I'll send you this one. It probably will be tomorrow morning before I'll get this processed, and then I'll post it on that same exact link page that I sent you before.
Okay.
Okay? All right, Grace. I will talk to you next time. And incidentally, when you were asking me about times available, the easiest way to find my availability is to go to my website, and it'll tell you every exact opening I have. Notice how difficult it would be to try to describe to you what my available times are in this schedule. Because there's just all kinds of... There's all kinds of...
write down your thing.
Let me do this. Here. You don't need to write it down. I will copy and paste it. In fact, there's my website, but let me go to schedule appointments. So this link here will allow you to see all of my availability. and schedule the appointment. You see the link in the chat window?
Yeah.
Go ahead and click on it.
Okay.
And then save it as a favorite on your computer so that you can always get back to it. And the way you see my availability is you go down and click on Book Now. In other words, if I click on that Book Now, if you're looking for an hour session, click on the 1 hour.
Okay, wait a minute. Click on the Book Now button.
Uh-huh.
Oh, there it is.
Okay. And then click on 1 hour, and it'll give you a calendar. You can pick a date. If I look at my availability on Friday, the 7th, it's going to show you a lot of times available. You can pick any of those times, and it would be an hour from the beginning of that time.
Okay.
Okay? And that's the easiest way to do it, just because it's a lot easier for you to read my availability off of a calendar than it is for me to try to describe it.
Okay.
All right. All right. Well, it was good working with you. I'll talk to you next time.
Okay, thank you.
Bye-bye.